Hello children, once again welcome back to Physics with Sanob. So in this video we will be discussing the past questions from the chapter Thermodynamics. See, we will be discussing all previous questions of NEET and before that AIPMT. Okay, now let's go to the first question. 1 gram of water of volume 1 centimeter cube at 100 degrees Celsius is converted into steam at the same temperature under normal atmospheric pressure 1 into 10 raised to 5 Pascal. The volume of steam formed equals 1671 centimeter cube. If the specific latent heat of vaporization of water is 2256 joule per gram, the change in internal energy is. See, work done delta W is P times delta V. And original volume was 1 centimeter. When it is converted into steam, the volume is 1671. So the change in volume will be 1670 centimeter cube. Can be converted into meter cube by multiplying with 10 raised to minus 6. So work done will be 167 joule. See, this is first law of thermodynamics. Delta Q equal to delta U plus delta W. Delta Q is the heat absorbed and delta U is the change in internal energy. Okay, and change in internal energy will be delta Q minus delta W, that is 2256 minus 167, and it will be 2089 joules. Okay, now let's see what we have next. A sample of 0.1 gram of water, 100 degrees Celsius and normal pressure requires 54 calorie of heat energy to convert to steam at 100 degrees Celsius. If the volume of steam produced is 167.1 cubic centimeter, the change in internal energy of the sample, P delta V, again work done, that we will get 17 joule, and delta Q is 54 calorie. 1 calorie is equal to 4.186 joule. So 54 calorie will be 4.186 into 54, that is 226. So change in internal energy delta Q minus delta W, and it is 209, or let us say 208.7 nearly, right? Next, a system is taken from state A to state C by two paths ADC and ABC as shown in figure. Okay, the internal energy at A is U with the suffix E, that is equal to 10 joule. Okay, along the path ADC, the amount of heat absorbed delta Q1, okay, that is equal to 50 joule, and the work done delta W1, that is equal to 20 joule. Whereas along the path ABC, the heat absorbed delta Q2 equal to 36 joule. The amount of work done along the path ABC. See, this internal energy is a state function. So as the system is taken from the state A to the state B to the state C, internal energy, change in internal energy will be independent of the path followed. So if we take the system along the path ADC or ABC, in both the cases change in internal energy will be the same. Okay, now let's first consider the path ADC. Delta Q is delta U plus delta W, and the heat added in the first case, that is 50 joule. Okay, delta U, that is plus work done, that is 20 joule. Okay, delta W1, right? So delta U will be 30 joule. So delta U, the change in internal energy when the system is taken from A to C, that is 30 joule. It is independent of the path followed. So if you take the system along the path ABC, then also change in internal energy will be same, that is 30 joule. Now consider the path ABC. Okay, the heat added is 36 joule. Okay, the change in internal energy will be 30 joule, and work done will be delta W, we have to, the amount of work done along the path ABC, that must be 6 joule. Okay, this one. An ideal gas follows a process described by the equation PV square equal to constants. PV square equal to constant means pressure is inversely proportional to square of the volume. So when P1 is more, V1 should be smaller than V2. But here it is given that P1 greater than P2 and V1 greater than V2. That cannot be true. Okay. Now next see we have a relation between pressure and temperature. Okay, now see PV square equal to constant, that is true in this particular case, and PV by T is NR, that is constant for an ideal gas under any condition. So from these two, if we eliminate volume, see we will get the relation between temperature and pressure. Pressure will be directly proportional to square of temperature. Okay, so when P1 greater than P2, T1 greater than T2. But here it is given that P1 greater than P2 but T1 less than T2. That's also wrong. Okay. Now see, if we eliminate pressure from these two equations, we will get the relation between temperature and volume, and we will get TV equal to constant, or temperature varies inversely with volume. Means when V2 is greater than V1, then T2 should be smaller than T1. Okay, so V2 greater than V1, then T2 greater than T1, that cannot be true. Okay, and finally when V2 greater than V1, T2 less than T1, that can be true. That is the only statement it can be true. Okay, among the four, right? Next, an ideal gas undergoes four different processes from the same initial state as shown. These processes are adiabatic, isothermal, isobaric and isochoric. Okay, the curve which represents the adiabatic process, children, this is with the constant volume, isochoric. This is with the constant pressure, isobaric. Okay, this one with the constant temperature or isothermal, and this is adiabatic process. So adiabatic process is represented by the curve 2. Okay, now why it is adiabatic? See, for an adiabatic curve, see the slope is given by gamma P by V, and for isothermal it is P by V only. Okay, both the slopes are negative, and see the slope of the adiabatic curve will be more compared to the slope of the isothermal curve, or adiabatic curve will be steeper compared to the isothermal curve. Okay, now see the curve 2 represents adiabatic process. Now in which of the following processes heat is neither absorbed nor released by a system? The process must be adiabatic. Okay. Now see the volume V of a monoatomic gas varies with the temperature capital T. See, as the volume versus temperature graph is a straight line passing through origin, V is directly proportional to temperature in an ideal gas. See, that will be true only if the pressure is constant, or let us say the process is isobaric. When some heat is added to an ideal gas at constant pressure, a part of it will be used to increase the internal energy. What fraction of heat added is used to increase the internal energy? See, that is delta Q NCP delta T is the heat added, of which delta U NCV delta T is the heat that is used to increase the internal energy. Then the fraction delta U by delta Q, that will be NCV delta T by NCP delta T. N delta T will get cancelled, so we will get CV by CP, and it is 1 by gamma. See, if 1/3 of the heat added is used to increase the internal energy, then the rest means 1 minus 1 by 3. 2/3 will be used for external work. Okay, similarly, here the 1 by gamma, that is the fraction used to increase the internal energy. So 1 minus 1 by gamma, that will be the fraction used for external work done. Okay, so we will get, see children, we have gamma equal to 1 plus 2 by F, where F is the number of degrees of freedom. Here the gas is monoatomic, so the number of degrees of freedom is 3. So we will get 1 plus 2 by 3, or it is 5 by 3. Delta W by delta Q, that is 1 minus 1 by gamma. Gamma is 5 by 3, so 1 by gamma is 3 by 5. So we will get 1 minus 3 by 5, or 2 by 5. First option. Now see, figure below shows two paths that may be taken by a gas to go from state A to state C. In the process AB, 400 joule of heat is added to the system, and in process BC, 100 joule of heat is added to the system. See, when the system is taken from the state A to the state B, the process is isochoric or at constant volume, so the work done will be 0. But it absorbs a heat 400 joule. Okay, when the system is taken from B to C, the process is isobaric and it absorbs 100 joule of heat. So the total heat absorbed when the system is taken from the state A to the state C is 500 joule. Okay, work done during the process AB is 0, but there will be some work done during the process BC. See, the pressure here it is 6 into 10 raised to 4 Pascal. And the change in volume is from 2 into 10 raised to minus 3 to 4 into 10 raised to minus 3. Or 4 minus 2, that is 2 into 10 raised to minus 3 meter cube. So the work done will be P delta V in isobaric process. So 6 into 10 raised to 4 into 4 minus 2 into 10 raised to minus 3. See, here it is 4 minus 2, 2 into 6, 12. Okay, 10 raised to 4 into 10 raised to minus 3, that is 10. So we will get 120 joule. So when the system is taken from A to C, the change in internal energy delta UAC, that is equal to delta Q minus delta W. So 500 minus 120, that is 380 joule. As this internal energy is a state function, when the system is taken between two given states, change in internal energy will be independent of the path followed. So if we take the system directly from A to C, then also the change in internal energy will be same as before, that is 380 joule. Now let's find the work done during the process AC. See, this is the process AC. So the area under the graph will be the work done, as this is a PV diagram. Okay, here the area is a trapezium. Okay, so work done will be average of the parallel sides. See, these two are two parallel sides. Okay, and see what is the average. Here it is 6 into 10 raised 4 and here it is 2 into 10 raised 4. So half of 2 plus 6 into 10 raised 4. And see, separation between these two parallel sides, that is this much. Okay, and it will be from 2 into 10 raised minus 3 to 4 into 10 raised minus 3, or let us say 2 into 10 raised to minus 3. Okay, so 4 minus 2 into 10 raised minus 3. And this we will get 80 joule. So the heat absorbed when the system is taken directly from A to C. By first law of thermodynamics, it is delta W plus delta U, and that is 80 plus 380, that is equal to 460 joule. Okay, so this must be the correct option. A monoatomic gas at pressure capital P having volume V expands isothermally to a volume 2V and then adiabatically to a volume 16V. See, when the process is isothermal, PV equal to constants. Product of pressure and volume, initial and final, will be the same. Okay, so initially pressure is P, volume is V. Finally, when it is expanded isothermally, the volume is 2V and pressure, let it be P1. So we will get P1 equal to P by 2. When it undergoes an adiabatic expansion, P1 V1 raised to gamma, okay, initial condition, that will be equal to P2 V2 raised to gamma. Okay, and V2 is given as 16V. Okay, P2 over P1, that is equal to V1 over V2 raised to gamma. V1 is given as 2V and V2 is given as 16V. So it will be 1 by 8 or 1 by 2 cube. Whole raised to gamma, that is given as 5 by 3. So 1 by 2 raised to 5 or 1 by 32. So P2 will be P1 by 32. And P1 we have initial pressure by 2. So it will be P by 64. This must be the correct option. Now, during an adiabatic process, the pressure of a gas is found to be proportional to the cube of its temperature. The ratio of Cp by Cv for the gas is T raised to gamma divided by P raised to gamma minus 1 is constant for an adiabatic process. And we can write P directly proportional to T raised to gamma by gamma minus 1. And here it is given that pressure is directly proportional to cube of temperature. Means gamma by gamma minus 1 is 3. And from here you will get gamma equal to 3 by 2. Okay, 3 by 2. So gamma equal to 3 by 2. Right? Heat rejected by the gas during the cyclic process. As the process is cyclic, change in internal energy delta U equal to 0. Okay. And what about the work done? Delta U equal to 0. See, work done is the area enclosed by the PV diagram. And see here the area, children, it is traced in the counterclockwise direction. So work done will be negative as it is traced counterclockwise. See, the change in volume is from V to 3V, that is 2V. Okay, 2V. And this is from P to 2P, that will be P. So the work done will be, work done will be P into change in volume is 2V. As the area is traced counterclockwise, work done is negative. So minus 2PV. Okay, minus 2PV. As delta U equal to 0, delta Q equal to delta W, and it is minus 2PV. See, so delta Q negative means heat is released by the system. Okay, so heat released. The heat rejected by the system is 2PV, right? Now, during an isothermal expansion, a confined ideal gas does 150 joule of work against its surroundings. This implies, see, delta Q equal to delta U plus delta W by the first law of thermodynamics. Delta U equal to 0 as the process is isothermal. No change in temperature. So internal energy, as it depends only on temperature, here it will be constant. Delta U equal to 0. So delta Q will be delta W, and it is 150 joule. Means that much heat will be absorbed. Okay, or 150 joule of heat has been added to the gas. Okay. Now let's see a mass of diatomic gas gamma equal to 1.4 at a pressure of 2 atmosphere is compressed adiabatically so that its temperature rises from 27 degrees Celsius to 927 degrees Celsius. Children, this is the initial temperature. 27 degrees Celsius means 300 Kelvin. And this is 927 or 1200 Kelvin. Okay, here we have gamma 1.4, it is 7 over 5. Gamma minus 1 will be 2 by 5. Gamma by gamma minus 1 will be 7 by 2. Okay, we have for an adiabatic process, T raised to gamma by P raised to gamma minus 1 equal to constant. Or we can say P directly proportional to T raised to gamma by gamma minus 1. Okay, or P dash by P equal to T dash by T whole raised to gamma by gamma minus 1, and that is equal to 7 by 2. See, T dash is 1200 and T is 300. So 1200 by 300 will be 4, or it is 2 square. So we will get 2 raised to 7. Children, 2 raised to 5 is 32, 2 raised to 6 is 64. So 2 raised to 7 will be 128. Okay, so P dash is 128 P. And the initial pressure is given as 2 atmospheres. So the final pressure will be 128 into 2, that is 256 atmospheres. Now, an ideal gas at 27 degrees Celsius means 300 Kelvin. Compressed adiabatically to 8 by 27 is beautiful because it is 2 by 3 whole raised to 3. Okay. Of its original volume, the rise in temperature given that gamma equal to 5 by 3. Okay, gamma we have 5 by 3, gamma minus 1, 2 by 3. And V dash is given as 8 by 27th of its original volume V. Okay, see, in an adiabatic process, the relation between temperature and volume is T V raised to gamma minus 1 constant, or we can say T proportional to 1 by V raised to gamma minus 1. So T dash by T will be V by V dash raised to gamma minus 1. Gamma minus 1 we have 2 by 3. This 27 by 8 can be written as 3 by 2 whole raised to 3 whole raised to 2 by 3. So it will be 3 by 2 whole square because this 3 and 3 can be cancelled. Which 3? See, this 3 and this 3 can be cancelled. Okay, so 3 by 2 whole square, that is 9 over 4. Okay, so T dash will be 9 by 4T and T is 300 Kelvin. So we will get 675 Kelvin. We have to convert it into degrees Celsius. So you have to subtract 273. but never subtract 273. Instead of subtracting 273, you subtract 300. If you subtract 300 from 675, you will get 375. Then add 27. It will be 402 degrees Celsius. Okay. Now let's see what we have if the ratio of specific heat of a gas at constant pressure to that at constant volume is gamma. The change in internal energy of a mass of gas when the volume changes from V to 2V at constant pressure P is. Okay. See, delta U, that is the change in internal energy divided by delta Q, that we will get 1 by gamma. And delta W by delta Q will be 1 minus 1 by gamma, or gamma minus 1 by gamma. Okay, children, this 1 by gamma can be replaced by delta U by delta Q. So you will get delta U equal to delta W by gamma minus 1. And delta W is P into V final volume minus initial volume. So PV by gamma minus 1. So this must be the correct option. Next, a thermodynamic process is shown in figure. Okay, the pressure and volume corresponding to some points in the figure are given. Okay, in the process AB, 600 joule of heat is added to the system, and in process BC, 200 joule of heat is added to the system. See, during this process it absorbs 600, and during this process it absorbs 800. So from A to C through B, the total heat absorbed will be 800. And see, work done during this process is 0, but during this process there will be some work done. And let us calculate that work done. See, the pressure here, that is PB, that is 8 into 10 raised to 4 Pascal. And the change in volume will be from A to D. Okay, A to D, that will be 5 minus 2. Okay, that is 3 into 10 raised to minus 3. So the work done will be 8 into 10 raised 4, 5 into 10 raised minus 3, minus 2 into 10 raised minus 3, that will be 240 joule. Okay, as the system is taken from A to C through B, total heat absorbed is 800 joule and the work done is 240 joule. So the change in internal energy will be 800 minus 240, that is equal to 560 joule. Okay. Now the change in internal energy of the system in the process AC. See, the internal energy is a state function. So when the system is taken from the state A to the state C, the change in internal energy will be the same irrespective of the path followed. So if you take from A to C along the path, this one, or directly from A to C, or along these paths, in all the three cases, change in internal energy will be the same and it is equal to 560 joule. Okay.